Hi everyone, welcome to today's webinar, How to Boost Your Workforce with Invisible Start-to-End Bots. I'm Teresa Resick, Vice President of Market Intelligence at AIIM, and AIIM is your host and producer of today's event. And joining me today are Carl Hillier of Deep Analysis and Greg Council of Periscript. And Periscript is the underwriter of today's webinar, and we thank them very much for their support. And thank you for taking the time to join us. I'd like to introduce the speakers we have with us today. Carl Hillier is the Senior Research Director at Deep Analysis, an information and process management research and advisory firm. Carl has over 25 years in the enterprise software industry. He has an extensive background in ECM, information capture, BPM, AI, and cloud computing, presenting on these topics at conferences throughout the world. Carl's expertise has helped organizations such as Boeing, GE, UBS, and MetLife wrestle with the challenges of incorporating technology to improve the effectiveness of their business operations. And we also have with us Greg Council, and he is Vice President of Marketing and Product Management at Periscript. Greg has over 20 years of experience in solution development and marketing within the information management market. This includes search, content management, and data capture for both on-premises solutions and SaaS. And now to begin things off, I'm going to turn things over to Carl Hillier of Deep Analysis.
Thanks, Teresa. A number of years ago, I was at the AI Summit in London, and one of the speakers got up and talked about a survey that had been done recently of children, asking them about artificial intelligence and robots in particular. And the net result of the survey was a list of rules associated with AI. For those of you familiar with science fiction, you'll probably know about Asimov's laws of robotics. Well, these are children's rules relating to AI. Rule number 1, don't let bad people build robots. Number 2, always have an off switch. Number 3, don't put bombs on robots. And finally, number 4, don't make them look like us. Now, as humorous as this may be, it does serve as a reminder that AI and robotics and the proliferation of them in our society and technological landscape is a very powerful thing. However, like any powerful tool, it doesn't mean simply by using the tool that you're going to make things better. You could actually end up making things considerably worse. Now, to illustrate that point, I want to talk about a situation that arose last month in the United Kingdom, where thousands of high school students are awaiting their high school exam results. Those grades will have a profound impact on their lives, in that it will be through those grades that they attain places at their desired colleges and places on the courses that they wish to study. Now, the current COVID health crisis has meant significant disruption to the educational system in the UK, just as it has throughout the world. And this represented a major problem for the UK's Department of Education, because students were not able to physically take their end-of-year exams, upon which their grades would be based. So they needed to have a system to predict the students' exam results. And they looked to AI to help them achieve this. Now, they had to make a number of significant assumptions. One assumption was that the exam results, in broad terms, would be consistent with those of previous years. In addition to that, they needed to provide some additional inputs, and those would be provided by the students' teachers. Each student was provided an estimated grade by their teacher. So if their teacher thought that they would get an A, that was their estimated grade. And then they were also asked to rank all of the students within their class. So if I was taking a physics A-level in a class of 20 people at a given school, I would be given a ranking of 1 to 20. And then all of this information was put into an algorithm, and then that would generate my estimated grade. However, there are a number of things wrong with this approach. First of all, one of the assumptions here was made that the exam result would be consistent compared with previous years. And that might be true in aggregate, but obviously there are thousands upon thousands of students. Now, AI is used in a variety of different areas, notably within the realm of weather forecasting. Now, weather forecasts have got considerably better since the advent of artificial intelligence, the use of big supercomputers to predict the weather. And if I go into my Apple app, it will tell me the likelihood that it will rain at a given time in a given location. But it's providing an aggregate view. The most accurate positional information I can give is perhaps a zip code. And it will tell me maybe there's a 20% chance of rain in my zip code at a given time. But what it's not going to do is tell me a personalized forecast for me. It's not going to tell me how much rain is going to fall in my backyard at what time. So if I go out at 11 a.m., is it going to be sunny? If I put my washing out hanging on a line at 2 p.m., is it going to get rained on, and if so, by how much? It doesn't get down to that level of granularity. And of course, the problem here is that individual students are going to be dramatically impacted, even if their grade changes, say, for example, from an A to a B, or from an A to a C. That's going to have a significant impact as to whether or not they're able to go to their college of choice. And as you remember, the key assumption here was the fact that exam results will be consistent with previous years. So they're assuming, for example, at a given school, the grades received by the class from last year are going to be broadly the same as the grades that would have been achieved this year. And there are a couple of scenarios for which that doesn't work. Let's say, for example, I'm an extremely gifted student in a school that perhaps doesn't have a great track record. My grade is going to be dragged down by the performance of students from prior years. And in the same way, if you have a school that has consistently improved over a number of years, and in fact, in all likelihood, the results this year would be better than last year, that violates that assumption again. So again, a well-performing class of physics students is going to be dragged down by the performance of last year's class, which we've already established because the school is improving. We would expect better grades. But again, the algorithm isn't necessarily taking that into account. So when we look at the results from this, we see some very aberrant behavior, results that were not consistent with the overall objective. Now, if we look at the chart of the results, and here is a chart that shows the percentage of results that were changed, i.e. a teacher's prediction, and then what the algorithm came up with. So what we can see is about 58% of people, their grades were given as pretty much what their teachers said they were going to be. However, if you actually look, about 40% of students saw grades change by more than 1 point in the negative. That means that, for example, if I took 100 students that were all predicted to get A grades in physics, 35% of those would get a B, and just a little over 3% would get a C. And a very small number would actually get a D, even if the teacher had said they would get an A. And obviously that is a huge difference, because more faith was put in the AI algorithm than the teachers. The expectation was the teachers would perhaps be over-optimistic. But in reality, the teachers have spent 2 years with these students, teaching them this subject. And even if the most optimistic teacher is not going to recommend someone for an A, if actually in reality they're going to get a C or a D. So as we can see, this had very significant results. And a lot of that can be traced back to not trusting the teachers, and most importantly, the assumptions that were fed into the AI algorithm. This doesn't prove AI is wrong. The reason why these results were poor is because a number of the key assumptions that were made were inaccurate. So if you put bad information into an AI algorithm, it's not surprising that you get bad results. So what lessons can we learn here? Adding AI won't always improve the results. It may just cost you money. And in fact, what ultimately happened in the UK was the AI results were tossed out and the teachers' results were used if they were more reflective of the student's ability, or the student had the option of actually retaking an exam at some later date. But in some cases, that meant that students had to take a year out and actually start college a year later than originally planned. The second thing we learned is, think long and hard about these assumptions, because they will come back and bite you. AI will not miraculously turn bad data into good results. It will only do what you tell it to. So don't blame AI if you don't like the answers that you get back. In some ways, think of AI as a puppy. It's new and exciting. People assume that it will make everyone happy. Buy a puppy and all your problems will be solved. Your kids will be happy and everything will be wonderful. And that may be true. Puppies are eager to please. They're young. They want to learn. They love doing things for you. But most importantly, puppies require training, and AI is no exception. The training of AI has a direct impact with how productive it will be. And if you don't, it will create one hell of a mess. It's very important when you look at AI to make sure that you're applying it to a business problem where it adds value, and that you have sufficient data in order to train the AI so that that value can be truly realized. Now, I'm a bit of a movie buff. And back in 2015, there was a movie that was released called The Big Short. And it had a big ensemble cast. And it was about a whole bunch of characters that existed around the time of the mortgage crisis back in 2008. And one of the characters is played by Christian Bale, who's a gentleman by the name of Dr. Michael Burry. And Michael Burry was a really interesting guy. He was an MD. He had some inheritance money, and he started to invest it and ended up hooking up with an investment fund. And he was a very smart guy, and he was very laborious about how he went through systematically looking at information and looking for opportunities within the market. And he was the guy that really figured out just how perilous the mortgage market was. Now, one of the most pivotal points in the movie, and for those of you who are fortunate to have it or indeed go download it, about 14 minutes and 10 seconds into the movie, Michael Burry, having spent a lot of time reviewing all of these documents associated with these mortgage-backed securities, has a phone conversation with his boss, Lawrence Fields. Lawrence Fields had allowed Michael to invest money for his firm and been very successful at it. Michael Burry got on the phone to Lawrence Field when he realized just how bad the mortgage market was. And the conversation goes something like this. He's only a matter of time someone else sees this investment. We have to act now. And what he's talking about is these mortgage-backed securities are going to become junk. And Lawrence replies, well, how do you know the bonds are built on subprime crap? Aren't they filled with hundreds of pages of mortgages? And a mortgage-backed security is made up of all of these mortgages all lumped together as an investment vehicle. And this is the key thing. He said, I read them. He read all the mortgages. He looked at all the terms about when the interest rates were going to change and looked at the likelihood that these mortgages were going to be defaulted. And the response was, you read them? Nobody reads them. Only the lawyers who put them together read them. I don't think they know what they've made. The whole housing market is propped up on these bad loans. It's a time bomb, and I want to short it. Meaning that he wanted to place a bet that the market was going to die. And at the time, everyone thought this was absolute insanity. But part of the problem was that these mortgages have been put together and they've been rated by the rating agencies as AAA. And in a lot of cases, they weren't. And the way that mortgage-backed securities work is that if a small number of loans default, it's not a big problem. But if that percentage of defaults gets to a certain level, the losses outweigh the value of the stock. And therefore, what you end up with is worthless. And that's what Michael realized. He realized that if about 10 to 15% of these mortgages defaulted, effectively what was, in theory, a good, safe investment became completely junk. And that's part of the problem. There are a huge number of documents in the business world today where a lot of critically important information, like the terms and details of these mortgages, was simply not accessible. And that's what cognitive information capture is all about. It's not simply capturing the data, all of the text in a particular document. That's useful, but it's not very informative. What we want to be able to do is to actually pull out business structured data from those documents. Now, OCR, or optical character recognition, has been around for a very long time, far longer than people realize. The very first OCR systems were invented actually around 1914 as a means of turning letters on a page into either telegraph signals or audio tone to assist the blind in reading text on a page. But you need more than just a bucket full of letters or words. And if you want to try an illustration of what I mean, take a resume or some other kind of business document and go into Word and save that document as a text file. And what you end up with is something that, yes, you can read the words on the page, but it's very difficult to make out any kind of semblance of information. Now take something that, like, for example, like a spreadsheet that has a lot of structure, columns, rows, and so forth. What you're going to do is just get a whole bunch of numbers. They're not going to mean anything. And even if the columns have headers, it's really difficult to decipher what's actually going on. So what's needed is something far more sophisticated than merely OCR. And OCR is part of cognitive information capture, but there's a lot of other capabilities that have to be combined with that to really get us to the endpoint that we're looking for, namely giving us the structured business information that's actionable, that comes out of the processing of those documents. So cognitive information capture is a multi-stage process, and the first stage of that process is input. Where are the documents that we are going to be processing? So it's important to have omni-channel input, meaning those documents can come from a wide variety of sources and formats. So for example, some of these documents may already be electronic. They may be PDFs, they may be Word documents, they may be other types of electronic documents that contain business information. They could come from a physical file, they could come from a content repository, they could be stored in a network drive, they could also be inbound through email or fax. So it's important to be able to handle all of those different channels of input. We want to have image enhancement. So if we're dealing with things, for example, like a fax, where there could be distortion, a coffee stain, marks, handwritten annotations on a document, we want to be able to improve the quality of that image. And that's critically important because when we start doing OCR and extraction of information, we want that information to stand out as much as possible. We're dealing with both physical and electronic documents. For example, we may well have a PDF that is really a collection of scanned images of a document, but that's it. But if you've ever created an image, a PDF document from, say, Word, it also creates a text layer. So we already have a record of all the text. And what the image does is tell us how that text is geographically arranged on the page. And that's also important information when it comes to understanding what is contained within the document. The next stage, once we have our documents, is now we have to classify them. And that's important because by knowing what type of document it is, we now have a better idea of the information that we're looking for. So how do we classify a document? Well, first and foremost, if I were to stand presenting this in an auditorium and I held up my driver's license, I can guarantee that none of you would be able to read a single character on that driver's license, but you'd probably guess what it is. You guess because of the size, you guess because you can make out the patches of light and dark that indicate where things are. So for example, there's a photograph, you couldn't tell if it looks like me or not, but you could probably tell there's a postage stamp size photograph on the top left-hand corner. And if you actually looked at the text, and if I gave you a textual output of it, you would see certain words on that page that would indicate it's a driver's license, not least the two words driver's and license. But also there'd be other information on there that would be useful, like the state, in my case California, and other information. So it could be some kind of ID. Driver's license kind of gives it away, but there are other words that also would do that. So the fact that my height, weight, hair and eye color are on there, that's less likely to be on, say, some kind of corporate ID, but certainly is required on a driver's license. So once we know what a document is, we now know what the information it is that we're looking for, and that's going to allow us to apply the right kind of rules to look for certain phrases and so on within the document that allow for that information to be extracted. So now we know what kind of document it is, we want to be able to do some recognition. Now bear in mind we could be dealing with multiple pages, and we might be not handling one document, but multiple documents. So we could be having a batch of an application. There could be different documents within that. So we want to be able to identify the document beginning and end. So where does one document end and the next one begin? Things may have been faxed in upside down. So we want to orientate the pages correctly so that they're the right way up. Is it a portrait mode document, or is it landscape? And then we want to apply a whole bunch of technology to pull out all the information. So we're going to use things like optical character recognition, barcode recognition, OMR, which is optical mark recognition. There are certain marks on a page that can be used to pass information, but also to help us orientate where information is. We could use ICR to do things like constrained handprint or handwriting recognition. All of these things to be used can be pulling all of this information out, all of the textual information that's contained within the document itself. So now we know all of the characters on the page, all of the information in little pieces strewn across the page. What we want to be able to do now is to create structured data. So we're actually going to look for specific fields that make up that structure. So if you take a document, for example, like an invoice, we're going to want to know the invoice number. We're going to want to know the vendor name, vendor number, and various other pieces of data that are going to be on that invoice. Maybe not just the total of the invoice and the tax and the payment terms, but actually we might want to go down and look at the individual line items within the invoice, which will be a table of information. So we want to be able to pull all that information out, extract it, utilizing rules and having trained the system to recognize certain fields. So knowing, for example, that the invoice number is likely to be to the right of the word invoice. Now bear in mind, different invoices from different vendors are going to look different. Therefore, we can't simply say, look at this part of the invoice and create what I call keyhole OCR, where you imagine taking a black piece of paper and cutting holes out and then placing it over the top of a document and say, read through that hole, whatever's in there is the invoice number. With invoices, that's not going to work because there's a high degree of layout diversity. So therefore, what we need to be able to do is to use artificial intelligence and specifically machine learning to train the system to recognize all the different types of invoices to the point where ideally, if we see an invoice that we've never seen before, it's going to be able to pick that information up without manual intervention. Now, it might still happen, and that comes on in the next stage. So once we've pulled out all of the structured information from this document, we may be very confident. And we actually think, yep, you know what, we think we've got this 100% accurate. Our confidence threshold is high. However, let's say, for example, we do get a new format. Either it's a new vendor that's presenting an invoice for the first time, or perhaps it's a vendor who's decided arbitrarily to change their invoice format. The confidence thresholding, if sufficiently low, it's going to route that to an individual, a human being. And this is what we call supervised machine learning. So it's going to say, here is the invoice, here is my estimate of all of the information that I've been able to find. Maybe there's some information I can't find, or maybe I've found what I think is the invoice number, but I'm not totally sure. And then what supervised machine learning does is it sends it to verification, to an operator, who's going to look at the document and look at the information extracted and either confirm that the estimate of the AI is correct, or correct the information with the right information, or if it's not found anything at all, tell it where to look. Once it's done that, and this is very important, it not only then sends it off to be processed, but also creates a feedback loop where it's actually training the AI system on the fly, such that if there's another invoice comes in from that same vendor, because it's seen it already before and it's had its rules reinforced, the likelihood of that invoice being processed completely autonomously is greatly increased. Now that means the system is going to get smarter and smarter over time. Last stage in the process is output. So we've got all of this really useful information, but it's only useful if we can actually put it to work. So the last part of cognitive information capture is the output of that information. Obviously what we have is we have a document, and then we have some associated structured data. And we can put that, and that can be done in a variety of ways. It can go into line of business applications. So if it's an invoice, it can go into an accounting system. It could be going into external RPA systems, RPA being robotic process automation, which is going to do a whole bunch of repetitive things with that information. It could go into a BPM tool. The document itself may have to be put away into a content repository. So in a lot of cases, what you get is the document gets put into a content repository, a link to that document along with the structured information goes into the line of business application, so that someone now has access to all of that valuable structured data, either as a user, but also can be used to automatically process an invoice. So the invoice has come in, we have all the structured data, we can match it with the original purchase order, we can match it with the delivery note, and we can pay the invoice without it ever touching a human hand. But if we need to, we have the ability to go back to the original, because contained within the record is a link to that document in a content management repository. So what cognitive information capture provides is a mechanism that's highly scalable using a digital workforce, automating processes that historically would be very manually intensive. It's a process that gets smarter over time. It liberates the structured, actionable business data inside of documents. And ultimately, the more information you have, it also enhances the benefits that are realized and the return on investment of other intelligent automation technology, whether that be line of business applications, RPA, BPM, or other technologies that are used as part of a digital transformation initiative. So as you can see, it's not really enough to choose to deploy AI as some kind of silver bullet that's going to magically improve your business operations. The critical success failure is precisely how it is applied to address the right kind of business problem in order to maximize the likelihood of a positive business outcome. Now, I'll hand over now to my co-presenter, Greg Council, who'll discuss how Parascript exploits the unique capabilities of AI and machine learning in particular to deliver self-configuring software deployments. Greg, over to you.
Thanks, Carl. What I really like about Carl's presentation is the emphasis on the importance of establishing requirements, and of course, from requirements you get to focus on very important training data for machine learning. Without requirements, machine learning can't really work the way you expect it to. Machine learning, or the umbrella art of AI, really has no form until you apply it to a specific use case. And without those use cases and without a lot of planning up front, that puppy is going to make a mess of your house. So I am going to focus on software-defined systems and how that applies to intelligent document processing. So increasingly, Periscript, which is the company I work for, is using machine learning, including deep learning, not only to provide automation and refinement during production, but in using those same types of machine learning techniques to actually define what it is the software is supposed to do. And so we call that software-defined systems. So why do software-defined systems matter? If we're going to step back, we can look at how they actually emerged in the marketplace, and it wasn't actually software alone, but it was actually within the hardware world. For instance, networking. When you create a network made of physical equipment, the ability to easily reconfigure that network is pretty difficult. It's a pretty complex and error-prone process. So the industry created a much easier level of abstraction and chose to define the network architecture with software. And actually, the software could learn from usage patterns within the network and automatically configure itself. The benefit is that you spend less time focusing on those manual tasks of configuring and maintaining those configurations and more time using the network. And it's the same thing with software-defined systems. So with respect to intelligent document processing, it's really important because if you step back and look at what the focus of, what the true essence of why you want to use intelligent document processing is to get as much data out of document-based information as possible and do it in a way that's both precise and reliable. Precise meaning highly accurate, and reliable meaning that the system is able to determine when the information is accurate versus when it needs assistance from humans. And the reality is in today's world, even now, with machine learning technologies and computers that you can speak to achieve a high degree of precision and reliability for intelligent document processing takes a lot of work. If you were to line it up, line all the different tasks up, it would take over the entire slide set that I'm presenting here, but I'm boiling it down to some main tasks. So if you're dealing with images, certainly intelligent document processing came from the imaging world, but now it encompasses digitally born documents. But if you're dealing with images, you have to do a lot of configuration around how you account for image quality, documents that are scanned or documents that are transmitted via fax. You have to create rules around how you identify one document from another. And within all of this, you've got this iterative process of testing and refinement, all the way through locating text and then reliably outputting it. And I have this really important 6th stage that says once you do it all, you continuously have to maintain it every time you add a new document or a new document variant. And what this ultimately represents is a lot of tasks that are expensive and more expensive than most organizations can actually perform. So the reality is that there are a lot of organizations out there that are using intelligent document processing that while it has met a good amount of performance, it in no way represents the full state of what the software could do. So let's look at this underlying cost and complexity problem from a couple of angles. This first one is the kind of a cost profile. So if you were to map the effort it takes to achieve a high rate of precision, you're going to see initially, to get about 50% of automation. So what that means is 50% of your document tasks automated to a reliable level that they can go straight through. it's not going to take too much of time, but still takes a lot more time than most organizations see. So here it's around 10 man months, and of course all of this is dependent upon the nature and the complexity of your documents and the range of documents and what you really want to do. But this is a really good general illustration. But really the important thing is most organizations want to automate not 50% of their tasks, but 100% of their tasks. And when you start moving up this curve to 60% and then 70% and then 80% automation, you start to encounter a lot of headwinds. It's kind of similar to the process of moving a car from 60 miles an hour to over 200 miles an hour. You have to practically double or triple the amount of horsepower it takes because of all those headwinds and everything dealing with friction. And it's the same thing with software. So the amount of tuning and the attention that you need to do and the number of samples, input samples you have to use to get to that level of refinement is just more expensive than what most organizations can really undertake. And looking at it from another perspective, we all know that now that intelligent document processing is not it's just a means to an end. It is not the end unto itself. So no one organization purchases intelligent document processing just to automate document-oriented tasks. You're using it to provide a lot higher level access to this information so that it can be used in all sorts of business processes. So intelligent document processing really, if you look at it from a license spend perspective, should represent only a small fraction of the total expense. So here we have, a pie chart that roughly correlates to most implementation projects where you have a lot of expense in the integration. That's to be expected because, again, the software doesn't exist by itself. You've got enterprise content management that helps with case management and stores the documents and enables them to be retrievable. You've got the process management piece of it, and then you've got the intelligent document processing expense of it. But when we look at it from a professional services spend in terms of where the focus it should be if you need to achieve a high level of automation, and certainly organizations expect that, you have this almost outsized spend required on the intelligent document processing side to achieve high levels of automation. And the reality is this really never occurs. I mean, when you're looking at a project implementation from an implementation cost perspective, it's not quite that even. And it definitely shouldn't be, you shouldn't spend as much as 35 or even remotely close to that on the intelligent document processing side when it is only a fraction of what your business process is, and definitely it's not the most important thing within it. So ultimately, what this has led to is this rather unfortunate trade-off, a trade-off in terms of using out-of-the-box functionality and relying upon it heavily, where you have, you don't have to spend as much time on the complex configuration and refinement, but the capabilities are really limited to what has been built. If you need to deviate any amount in terms of adding support for new document types or different field levels or different levels of validation, or if your accuracy requirements deviate from what's provided within this out-of-the-box capability, you're really forced into this other path, which is a complex custom project that is pretty expensive. So this is really not a good thing to have. You're either forced into one very overly simplistic one-size-fits-all type of path or a very bespoke type of path. And this is where software-defined systems really come into play with the use of machine learning technologies. So I'm sure you are probably being exposed to concepts such as the quote-unquote citizen developer or software that is low-code or no-code. And all of this is really an effort on enabling a wider audience of end users to be able to configure software that doesn't require software development skills. And this is a really good thing. And also much in the market has been, they've talked about applying machine learning, in order to identify patterns and things like that. But the reality is To achieve a low-code or no-code capability, you can apply machine learning to the whole process of configuration itself. And this enables a really cool shift from focusing on implementation of configuration of different rules and things, and it allows you to shift focus on refining your requirements, really understanding what types of things you want to automate, and then the necessary data, collecting that all-important training data that you use to automate the process. So I'm sure that everyone has been exposed to these types of facts around the levels of success of IT projects, right? Where more than 50% of IT projects fail at some level. And really, when you start to peel back everything, one of the root causes is just a lack of time spent on really nailing the requirements and then really nailing all the inputs that are involved in successfully implementing any type of IT project. So if we were to look at it from a traditional versus a new perspective, the top one is the traditional, where you've got this input data that you're always needing in order to identify how you should go about automating a certain task. And in the middle, you've got this software development piece of it. And this is really where the focus is on development. People want to race to actually start writing code. And then, of course, you've got the output being the software that's developed. It's been tested, and it's met arguably all the requirements on the front end, if all those requirements are accurate. The new model actually allows you to place more emphasis on getting your input data. So it's the requirements and it's all the data that you're using to train these machine learning algorithms. And then the machine learning piece of it does the analysis of what your business processes are and your requirements and the data, and the output is software. So that's a software-defined system. And it's a very similar thing when we're talking about intelligent document processing. So on the top one, we have input data. So these are all your documents, and you've got your requirements of what you need to do. So if it's document classification, you're creating rules and things like that. But there's an intense focus on configuration and testing, or at least there should be. You recall these preceding slides that point out the fact that no organization actually spends enough time on it. But arguably, this is where you should be spending most of your time, which is really all that cost and complexity. And the output is configured software that's designed or configured to automate the tasks that you specifically need. So whether it's mortgage or loan file classification or validation of data within it, or you're within an insurance type of process where you're automating prior authorization or analysis of patient records, that is the ultimate goal there. So on the bottom side is the new piece of it, and it's the same way as software-defined systems. You have machine learning analysis in the middle, and all of this is done for you, and it allows you to focus on just getting the requirements and those input data sets just right, so that they're representative and they're comprehensive in terms of representing the data that you really want to automate, and the output is configured software, optimized to your specific use cases. So you kind of see the story here of, through the use of or application of machine learning, not only is it a benefit when you're using it in production, but we can move it forward or pull it ahead and actually use it to dramatically simplify the configuration process without sacrificing precision. It is literally a case of having your cake and eating it too. So let's dig into a little bit on how it works within the IDP world, how this self-configuration works. So if you look at any type of modern machine learning system, you need to train it. So I think everyone has looked for images on the web using Google image search or something similar. But in order to get really good results in terms of what you're trying to find, for instance, if we're looking for a cat, at a very minimum, this is a very basic level, to train the system to reliably locate cats within images, you need to have images tagged with cats. Right, so you have a set of images where it's got cat present, and then you have all other images that represent kind of the opposite of that, not cat present. And you train the system, so the system analyzes all of what we call features of these images that would indicate reliably if a cat is present. So it's looking at the shapes and the colors and all those types of things that are common across literally millions of different images of cats and images without cats to be able to distinguish at a reliable rate what images have cats in it. So it appears magical at the very end, but the reality and the power is that these machine learning algorithms can crunch enormous amounts of information and see things, see these features that we might not see at all. And that is really a cool concept. So when we apply this to IDP, we're doing a similar thing, except we're not doing answers for cats and not cats. What we're doing is we're taking a data set, which is in this case documents, and we're doing things like clustering them by likeness. And we're doing things regarding automated detection of certain features such as presence of handprint or paragraphs of text or tabular data or even non-textual types of features like logos and signatures and variability of fields and all these different types of analysis that will allow a system to be able to reliably classify one document from another. So we're not looking at features like ears and whiskers and colors, but we're taking the attributes of document-based information and using those to train the system. And for data extraction, it's a similar process. The difference being is we're not inputting documents in their classes, but we're inputting documents. Say, for instance, this is an invoice, and we have the tags or the metadata indicating the values of the data we'd like the system to learn how to reliably locate and extract. And from there, it's looking at more text-based analysis such as, fonts and font sizes and the location of the data, the proximity of one data element to another. Is there a reliable presence of keyword value pairs? All these types of things that arguably, if you're going to embark on a project and configure this manually, represents a significant amount of work because you've got to do this not only for one variant, but for all the variants. And the power with machine learning, again, is it can take these input data sets and discover all of these attributes, whether they're known to us visibly or unknown to us. And it can use those to calculate what is more reliable. Ultimately, the output is a highly optimized system that's pretty comprehensive in terms of its ability to operate on documents, even documents that it hasn't seen before. And there are other benefits. So apart from the ability, once you acquire the software, to automate a lot of this expensive, time-consuming, complex configuration, you don't have to learn how to configure the software. So while all IDP software is meant to do a similar thing, different software behaves different ways, and it's ultimately all complex. But when you can rely on machine learning algorithms to configure the software and optimize it, it allows you to have a greater level of reliability in proofs of concepts and evaluations of different vendor software. So if it's really about precision, it's really not about identifying who's got the better user interface or identifying all these different features and functionality underlying it. It's really about understanding, can system A or system B produce more reliable, accurate output? And the benefit here is if systems provide you the ability to train on input data and automatically configure themselves, rather than focus on learning all these other types of things, it allows you to focus on the true nature or the true benefit of IDP, which is ultimately you'd like to be able to compare system A to B to C based off your data and focus on the output side of it, not on all these intermediate stages of the complex configuration, everything like that. So you can run POCs in a shorter amount of time without the typical requisite complexity and staff drain that it usually takes, and get a higher level reliability on the output side. So I've covered a lot of things here, but they can really be boiled down to four main takeaways, which is, the first one, in the modern era, quality training or test data is the new imperative. If you don't have it, you're going to be lost when it comes to utilizing machine learning and applying it to whatever use case. It doesn't even have to be with document-oriented data. If it's a structured data set, but you still want to apply analysis on it, you need really good representative data. Otherwise, you're not going to get any kind of meaningful level of automation or insight out of it. And when machine learning is applied, so the input data need is always there, whether you're doing it manually or not. But when you use machine learning, it is the true meaning of the garbage in, garbage out. And we've all seen evidence of that, and Carl provided a great illustration of if you have biased input or training data and you don't have your requirements just right, then the output side of it is going to be a mess. The third one really is around, even though the value of data curation, you can't overstate the value of this. Data is the new gold when you're applying machine learning algorithms to solving your problems. It's relatively a fraction of the cost of having to learn software and spend the time configuring it and optimizing it and maintaining it over time. So it's a trade-off I think any organization should be hands down willing to take on. I would rather trade the hundreds of thousands of expense that I have with initially configuring the software and maintaining it for literally the single $1,000 type of effort it takes to gather information, analyze it, and make sure that it's representative of your larger data set. And the cool thing is there are tools to automate that process too. So it becomes a really, really good thing. And I mentioned that it is literally like having your cake and eating it too. And the last one, of course, if you haven't gathered by now, if you don't have that data and you're planning to use any type of machine learning, then you're already behind. So the best thing you can do to prepare for any type of project is not only look at the requirements and make sure that those are solid, but make sure that the data that you're going to use to configure a system, even if it's manually, is representative and it's of high quality and you've got that metadata associated with it. Having that ready to go means that everything else is going to be a lot simpler and a lot more straightforward and definitely a lot more reliable. And for either part of the presentation, if you have any questions, here is the contact information here, and we'll be happy to answer any specific types of questions. I can tell you that there's been a lot of interest around how many samples, for instance, or how do you curate data, so much so that we're probably going to do another AIIM webinar focused solely on this topic, so be on the lookouts for that.
We'd like to thank our speakers, Carl Hillier of Deep Analysis and Greg Council of Periscript. And I very much want to thank our underwriter, Periscript. Without support from our solution providers, AIIM wouldn't be able to bring you these free educational programs like our webinars. And thank you very much for taking the time to join us and to listen to this presentation. For AIIM, this is Teresa Resick, and we will see you at our next event. And have a great day.